While working from home during the pandemic, we all got a crash course on video meetings. As we return to the office, those simple video conferences get much more complicated in the meeting room. With Barco ClickShare Conference, you need one click of a button and your laptop is connected to all the room equipment wirelessly, and you're online with your remote team using any conferencing platform such as Zoom or Teams. To see how we've made this so simple, schedule your free live demo today at experienceclickshare.com. Ever drive an EV? You'd know, because once you feel the thrill of electric, there's no going back. And the next generation of EVs by General Motors are an absolute joy to drive. Imagine an EV that can go from 0 to 60 in an estimated 3 seconds. And fully electric means you can feel good about feeling that thrill. This pleasure will be made possible by Ultium, a revolutionary new EV platform from GM that keeps the good times going. Discover the thrill that awaits at gm.com. Everybody in. Welcome to Tech Stuff, a production from iHeartRadio. Hey there and welcome to Tech Stuff. I'm your host, Jonathan Strickland. I'm an executive producer with iHeartRadio and I love all things tech. And I end nearly every episode of Tech Stuff asking y'all if there are any topics you'd like to hear me explain on the show. And recently, a lot of you have been sending in requests, which is awesome. And I'm getting to those now that those tech glossary episodes are all done. And first up is a message from Brian Perez, who wants to know about fast charging technology, which is a great and legitimately confusing suggestion because there are a lot of different technologies out there. So today we're going to talk about how batteries work, because that's important for us to understand this technology. Then we're going to talk more about how rechargeable batteries work, because clearly that's going to be important. And then we'll talk about what makes fast charging possible and some of the different technologies that are out on the market and why it's such a mess. So let's do that. And we'll start with the basics of electricity and that lovely equation that tells us that wattage, that's a measurement of power, is equal to current in amperes times voltage or volts. And it's good to remember the difference between current and volts. Current refers to the amount of electric current moving across a circuit, and voltage is the force that drives that current. So frequently, folks like me use the analogy of water pressure to describe voltage, and the amount of water actually flowing through a system to describe current. So voltage is sort of the oomph at which current gets pushed. We'll come back to the wattage discussion toward the end of this episode because that's really at the heart of fast charging technology. So let's talk about how batteries work in general and the evolution of the battery. Now, one thing we have to keep in mind is that batteries don't create energy. Energy can be neither created nor destroyed. Batteries store energy in the form of chemical energy. They release energy in the form of electricity. So we're really talking about converting one type of energy into another. That is possible, right? We can't create or destroy energy, but we can change it from one form to another. So that's the heart of what batteries do. Batteries go through an electrochemical reaction, and through that process, they release electrons, i.e. electricity. The reaction takes place and electrons are a byproduct. They are released as part of this chemical reaction. Even when a battery isn't being used, this reaction can still occur, though typically at a very much slower rate, right? Otherwise, batteries would be dead before you ever got a chance to use them. But it does happen. This is called self-discharge. This is one of the factors that determines the shelf life of a battery. So if you ever look at just a long list of all the different types of batteries, you'll typically see the listed, average shelf life of them. And if it's a shorter shelf life, that tells you that there's a higher rate of self-discharge. Generally speaking, that's actually being a little too reductive because it also depends on the capacity of the battery, like how much volume does the battery have. But we're not going to dive too deep into all of that. So batteries that are in hot environments also tend to self-discharge at a faster rate than batteries that are in a colder environment. So you don't want your batteries to be in some place that's going to be really hot. However, this also leads some people to make a decision that is not very wise. It is not a good idea to shove, unused batteries in the freezer so that you can make them last longer. The lower temperatures that the batteries experience, that means that it will impede the chemical reaction when you plug it into something. So this means that a cold battery will not perform as well as a normal battery until it gets up to temperature. And when I say that a battery will eventually go dead through self-discharge, often we are talking about a factor about years, right? So self-discharge doesn't happen overnight. There's no reason to put batteries into the fridge or the freezer or anything like that, because you're likely going to use them before they would have self-discharged anyway. Setting aside stories about, ancient Babylonian containers that might have been used as some sort of proto-battery, possibly for the purposes of electroplating materials, the ancestor of the modern battery really took shape in 1799 with Alessandro Volta, and his name gives us the word volt. More importantly, our history starts with a disagreement between two scientific thinkers. And those thinkers were Volta and Luigi Galvani. Now, Galvani had observed in the 1780s that if he were to take a frog that was really most sincerely dead and expose said dead froggy's leg muscles by, cutting away the skin, and then touching that muscle with an arc made from iron and brass, it would cause the muscle to twitch. Now, Galvani had already run experiments using things like an electrostatic generator, so a device that generates an electrostatic charge. And he knew that there was some connection between muscular movement and electricity because of this. But this was different, right? Because he was using what appeared to be an inert pair of metals. It was iron and brass, and there was no electrostatic machine generating a charge. He wasn't even doing this during a thunderstorm. He had observed that thunderstorms could also produce electrostatic charges that could then influence experiments like these. But this was a case where neither of those things were components. So he said, the electricity must reside within the muscle itself. If it's not in the iron and brass, it's got to be in the muscle. And Volta thought that his buddy Galvani was totally on the wrong track. Volta's assertion was that the cause of the twitching was due to the use of two different metals that were connecting to one another through the medium of a moist conductive substance, that being the froggy's leg muscle. So Volta decided to experiment in the field of electrochemical reactions to see if perhaps he was right and if Galvani was wrong. So Galvani, by the way, was totally right in that muscle movements are the result of electrochemical processes. But in this case, Volta was saying, yeah, but that's not what's happening here. I don't think you're making the right hypothesis. So Volta created a stack of material. He alternated layers of zinc. He then put in some cardboard that had been soaked in brine, and then he would put on layers of silver. So he kind of alternated with these, and he was able to create a kind of proto-battery that we refer to with the charming name of a voltaic pile. There were some pretty big limitations to this, however. The strength of this battery depended in part on the number of layers that he could build up. However, he couldn't make it too tall because the layers on top would start to press down so hard on the layers below that the brine in that cardboard would get squeezed out, and then it would suddenly be less effective. Also, the metal would corrode fairly quickly due to the electrochemical reactions, and the byproduct would build up on those plates, and eventually they would impede the reaction from continuing, and you'd see a decrease in electrical output because of it. Now, just a few decades after Volta's work, there was an English chemist named John Frederick Daniell who made or Daniel, I suppose. It doesn't have an E at the end, so I'll say Daniel. It's Daniell. He made an early battery using a plate of copper, a plate of zinc, and some gnarly chemicals. Let's see if I can paint a mental picture. So he took a big glass jar, and at the bottom of the inside of this jar, he put the copper plate. So the copper plate's at the bottom. On top of the copper plate, he poured in a solution of copper sulfate. By the way, these days, copper sulfate is used in stuff like herbicides because it kills plants pretty darn effectively. Also, when we're talking about batteries, we're often talking about chemicals that are acidic. That is pretty common. You've probably heard about battery acid, and it's one of the many reasons why you don't want to mess around, cutting open batteries and stuff. There are a lot of reasons for that, specifically when you get to things like lithium-ion batteries, and that's one of the many ones. So then on top of this copper sulfate solution, he poured in a zinc sulfate solution. Now, copper sulfate has a greater density than zinc sulfate. So the copper sulfate settled down at the bottom of the jar, and the zinc sulfate floated to the top. You've probably seen like mixtures of oil and water that do this kind of thing. Daniel then suspended a zinc plate within the zinc sulfate half of the jar. So imagine like a hook that hooks over the side of the jar, and hanging from that hook is a plate of zinc held horizontal above the copper sulfate level, right? So you've got two separate levels here and two separate sulfates. To each plate, he attached a conductive wire, and now we need a bit of an anatomy lesson for batteries. So let's consider your typical battery. Let's say that if you happen to have a battery nearby, you can even look at one and kind of get the lay of the land. So you've got two terminals with your battery. Like if it's a AA battery, it's on either end of the battery, right? These are the points of the batteries that connect to a circuit or a load. This is the pathway that electrons will take, where at some point along the way, they will presumably do some sort of work. So you've got a positive terminal and you've got a negative terminal. You could connect these two terminals directly to each other with conductive wire, but that's not a great idea. That would lead to the battery discharging very rapidly, and for some types of batteries that could be dangerous, as the battery will heat up from the rapid electrochemical reaction, potentially leading to combustion or explosion. So not a good idea to do this. Attached to the positive terminal inside the battery is the cathode. Connected to the negative terminal inside the battery is the anode. Together, these are the electrodes of the battery. There's a separator that keeps those two electrodes from touching. Otherwise, we would have a very similar situation to what I was talking about before, where you connect the two terminals with a conductive wire. Only in this case, it would be internal inside the battery as opposed to connected through an external wire. The separator does allow an electric charge to flow between the two electrodes. There's also a medium called the electrolyte that facilitates the flow of electric charge. So during discharge, the anode reacts with the electrolyte and experiences an oxidation reaction. Ions, that is, atoms or molecules that carry an electric charge from the electrolyte, will react with the anode, and that produces a new compound between the two, and in this process also releases electrons. So now we've got our supply of electrons. Popping over onto the cathode side, the cathode goes through a reduction reaction in which ions, electrons, and the cathode begin to form compounds. This process takes in electrons, while the process at the anode generates electrons, but the separator keeps the electrons from just rushing over from one side to the other, right? You would think, all right, if we've got an excess of electrons and like charge repels like, then the electrons don't want to be next to each other, right? They'd rather get to the other side, especially as that side grows more positive, because the electrons are negative and opposite charges attract. But the separator prevents the electrons from doing this. They can't get to that side unless you open a pathway for them. That pathway is the circuit. So when you open up a circuit, you create a circuit that connects between these two electrodes. Now the electrons have a way to get away from the negatively charged side of the battery and head to the positive charged side of the battery. And they will do that even if it means they have to do some work along the way. Thus, we have batteries. So with Daniel's battery, which we call the Daniel cell, the wire connected to the zinc plate served as the negative terminal. The wire attached to the copper plate at the bottom of the jar was the positive terminal. And the cell worked really well, but because we're talking about liquid components here, it couldn't really be used in any sort of application that the thing would be moved around because it would just be sloshing everywhere, right? So it had to be stationary. And that really limited what you could do with this kind of battery. A few decades later brings us up to the 1860s. That's when Georges Lechanche switched things up by making a battery out of a porous pot. He took some crushed manganese dioxide with a little bit of carbon in it, and he used that as the cathode. He packed that onto the inside of the porous pot. The anode was a zinc rod that was actually kept separate from the pot. So you had a pot on the inside of which was this mixture of manganese dioxide and carbon, and then you had this zinc rod. Then Lechanche put both the pot and the zinc rod into another container filled with ammonium chloride. That acted as the electrolyte. Now, this solution of ammonium chloride seeped through the porous pot to make contact with the cathode, and that allowed the electrochemical process to begin, and the carbon rod that would also be inserted into this pot acted as a collector for the electrons. So that's what you would use to, direct the electrons outward to whatever circuit. This type of battery saw widespread use in telegraph stations, but still relied on a liquid electrolyte. And that really made it unsuitable for stuff moved around a lot. So still not ideal. We would see all that change thanks to the work of inventor Karl Gassner from Germany. I originally put in my notes that he was a German inventor, but now that I read that, it sounds like he invented Germans, and I'm pretty sure they were around before him. Anyway, Gassner made several improvements to batteries, and that meant that they would be practical in many other applications. For one thing, Gassner had the bright idea to use zinc as the container material for the battery itself, so the body of the battery was made out of zinc, and it also served as the negative electrode. So it was doing double duty. It was the container and the negative electrode. So the actual body of the battery served as one of the two electrodes, the anode, in case you're trying to keep these things straight. Inside the battery, he put in a folded paper sack, which served as the separator, which kept the interior of the zinc case separate from the electrolyte. For the cathode, he used a mixture of manganese dioxide, and in the middle of this, he suspended a carbon rod, which again acted as the electron collector, and later he would add zinc chloride to the electrolyte because it reduced the rate at which the electrolyte would corrode the zinc of the case. It would then extend the battery's useful life by slowing down that process. But the most important part of this invention was that Gassner's battery is what we call a dry cell battery. It was not full of sloshy liquid, even though the electrolyte was sort of a jelly, liquidy kind of thing. The rest of it was all dry. It meant that you didn't have to worry about the battery components sloshing out all over the place. It meant that you could invert it and it would still work. It opened up a lot of applications for batteries. In the 1890s, the National Carbon Company, a US-based organization, developed the Columbia Dry Cell Battery, which was another improvement. They first started making Lechanche batteries in the 1890s, but again, those were wet cell batteries. An engineer at the company named E.M. Jewett created a 1.5 volt dry cell battery and got the blessing from the company to make a commercial version that they could actually sell. So in 1896, NCC began selling a 1.5 volt, 6-inch long dry cell battery. Interestingly, the National Carbon Company would buy a 50% stake in another company called the American Electrical Novelty and Manufacturing Company. The battery-making part of that company joined NCC, and together they became known as Eveready, and much later, that company would change its name to Energizer. So that one dates all the way back to the early 1900s. All of the batteries I've mentioned so far are what we call primary batteries. So a primary battery is a one-use battery. That means once the battery goes dead, it's really most sincerely dead. It's not coming back because We're talking about a different chemical component reacting with another chemical component to produce electricity, and then you get byproducts as well, and you eventually run low enough on those initial chemical components that you're not getting enough juice, and there's no way to reverse that process, right? Once it turns into the byproducts, the battery has become inert. Now, a few things that can happen to make a battery less effective. One is that, as I mentioned, you could have your chemical agents depleted in the battery. So what you've got now is essentially a container just filled with useless goop as a result of all these electrochemical reactions taking place. Another is that whatever you're using as an electron collector might get covered in deposits, and that blocks the collector's ability to collect electrons. And so you might still have some viable juice in the battery, but because of this corrosion coating elements inside the battery, it's not able to have that process go effectively. Corrosion is also an issue as well for the electrodes. If you've ever had an old battery in something and you've just seen this gross kind of buildup on it, that's often the corrosion I'm talking about. And all of these things lead to a battery's inability to produce current. With primary batteries, there's really no way to reverse this process. The electrochemical reactions will stop, and then you got to toss the battery. Primary batteries tend to be relatively inexpensive. They also tend to have a fairly long shelf life, but they're also wasteful. When we come back, we'll talk about secondary batteries, also known as rechargeable batteries. But first, let's take a quick break. Honey Nut Cheerios are made with whole grain oats and a touch of real golden honey. And they are totally delicious. Eating a bowl of Honey Nut Cheerios takes me back to my childhood, when I would think of them as a treat. But what's really cool is how well they treat me. Honey Nut Cheerios can help lower cholesterol as part of a heart-healthy diet. That's really important to me too. Over the past couple of years, I've really been changing my lifestyle to have a more healthy one. It's something that I kind of put off for far too long. And having something like Honey Nut Cheerios as a go-to breakfast is a huge mood boost, because I know I'm eating something that's healthy, but also something that I genuinely love and that's really tasty. And like I said, it takes me back to being a kid. When you start off a day like that, let me tell you, the rest of your choices to make sure you're on that healthy pathway are way easier to make. Learn more about Honey Nut Cheerios by picking up a box wherever you shop for cereal.
Today and every day, you're doing the impossible with so little time under so much pressure. And for businesses around the world, it's a real challenge, because increasing disruption comes with increasing complexity. It's time to rethink everything. Using hybrid cloud and AI, IBM is helping businesses take a scientific approach to invent, discover, and solve problems like no one else. Get a new perspective on working in today's world at ibm.com/think.
When I was talking earlier about the development of the battery, the last inventor I mentioned was Carl Gassner, who invented the dry cell battery, which was in 1885. But the rechargeable battery actually predates the dry cell battery, and the person who generally gets the credit for inventing them is Gaston Planté. No one invents like Gaston or imprints like Gaston. Okay, never mind. In 1859, he created a lead-acid battery that you could actually recharge. His battery's anode was made of a sheet of lead, and he used a sheet of lead dioxide for the cathode, and he placed a linen cloth between those two sheets. Then he rolled this into a cone-shaped spiral. He immersed this cone in a solution of sulfuric acid, which is pretty dangerous stuff, and the chemical reaction that resulted released electrons, and boom, you got yourself a battery. Gaston discovered that if he applied a charge to this battery so that current flowed into the battery, it would actually reverse the electrochemical reaction that produced the electrons. This battery then had a way to discharge and then recharge. In 1860, he presented a 9-cell battery to the French Academy of Sciences, and his peer, Camille Alphonse Faure, continued to work on the invention and saw it actually become a commercial product. Camille would later make improvements to this battery, including a process that would increase the battery's capacity for storing electricity. And we still use lead-acid batteries today. It's the type of battery you find in your typical internal combustion engine vehicle. So your typical car that has an internal combustion engine also has a lead-acid battery. Now, I mentioned that Gaston created a 9-cell battery, and that is something that we should chat about for just a moment. Some batteries, like car batteries, consist of multiple cells that connect to one another within the battery itself. So a typical car battery would have 6 cells connected in series. If you connect batteries in series, you increase the voltage that those batteries produce. Now remember, voltage is kind of like pressure. It's how much oomph is behind an electrical current. But it's not a measure of the amount of current itself. So you're not increasing the current by adding batteries or battery cells in series. You're increasing the voltage. If you add them in parallel, it's different. But we're talking about in series, one after the other. So your typical lead-acid battery has cells that individually have a voltage of 2 volts. But because they are connected in series, the battery overall has a voltage of 12 volts, right? You've got 6 cells, each 2 volts. You've got them in series, so it multiplies the voltage to 12. Most of your typical household batteries, like AA's, AAA's, C and D batteries, those typically come in at 1.5 volts. But again, if you connect them in series, you get more voltage. So a flashlight that has 2 batteries connected in series is actually relying on 3 volts for the voltage. Another thing we should touch on is that because batteries convert chemical energy into electrical energy, there's a fundamental limit as to how much juice a battery can hold. Now, that doesn't mean all batteries are equal. Depending on the materials used to create that electrochemical reaction, you can get more efficient and energy-dense batteries. For example, lead-acid batteries don't really have great energy density, which you typically measure either by comparing how much energy the battery can store compared to that battery's mass, or how much energy it can store compared to that battery's volume. There are 2 different ways of looking at it. Alkaline batteries, which make up a lot of the typical batteries we use today, the non-rechargeable primary batteries that we use today, those are better from an energy density metric, meaning based on that battery's mass or volume, it can hold more energy than a lead-acid battery. But we also have to keep in mind that these are much smaller than lead-acid batteries. A battery's power density and energy density depend on the mass and volume of the battery and the type of chemical components that make up the anode, the cathode, and the electrolyte. So we're ultimately talking about a chemical, physical process that relies on a limited amount of source material, like a limited amount of fuel, if you will. So this means that it's very hard to make longer lasting batteries based on what we have today. Unless you're making literally just larger batteries, you can't really squeeze more out of physics. It's just you're hitting the fundamental limits of what is possible in a chemical reaction. Now, in tech, we've got Moore's Law, which we generally interpret as meaning that every 2 years or so, the processing power or processing speed of computers tends to double. That's the very dumbed down version of Moore's Law, but that's kind of how we interpret it today. But we do not see batteries on a similar trajectory, right? We don't see batteries increase in capacity at the same rate as we're seeing processing speed or processing power. This is because the laws of physics don't really care if we need better batteries, which puts pressure on electronics manufacturers to really create ways to limit how much electricity gadgets actually require as they operate. Not just electronics manufacturers, but also, the companies that design things like operating systems. In order to make batteries last longer, you can't just build better batteries. That's a much slower process. It means that you have to be smarter with how much energy you try to access. So, barring some miraculous alien technology, we're not likely to see astronomical improvements to battery life. though there are people who are working on it. It's just we're not likely to see giant leaps there. So that means we just have to be smarter about how our gadgets access power. Often when we're talking about rechargeable batteries, we are thinking about mobile devices like smartphones, tablets, laptops, and handheld gaming systems and that kind of thing. These devices almost exclusively today rely on lithium-ion batteries. Now, if you were able to look inside a battery, and I urge you to never, ever, ever do this because there is dangerous stuff in those batteries, but you would see that the battery consists of layers of carbon, graphite, and lithium on the anode side. This is on the negative terminal side of the battery. And we refer to the arrangement of lithium that's kind of nestled between lattices of carbon graphite as intercalation. So they're intercalated between these layers. You can think of like the carbon graphite as being almost like a net, and the little lithium atoms are nestled inside between layers of this net. Lithium has 3 electrons, and you might remember from basic science class that electrons orbit the nucleus of an atom within certain energy shells, and that only a specific number of electrons can inhabit each shell. For the shell that's closest to the nucleus, you can only have 2 electrons. So that means that each lithium atom has 2 electrons in that first energy shell, and then there's a single lonely electron that's orbiting the nucleus in the next energy shell out from the nucleus. That also means it's pretty easy for lithium to give up that electron. It's not holding on to it super hard. That means the lithium atom, when it lets go of this electron, becomes an ion. It's a charged atom of lithium, a positively charged one in this case because it's given up an electron, which carries a negative charge, but it's held on to all of its protons, which have positive charges. So when a lithium-ion battery connects to a circuit, and that circuit becomes complete, the outermost electrons in the lithium atoms go through the pathway of the circuit and leave the lithium atoms, now ions, behind and head toward the positively charged cathode side of the battery. That's because the electrons carry that negative charge, and negative is attracted to positive. And the lithium ions left behind, they do have that positive charge to them. That'll become important in a second. Now, the cathode is positively charged because there is cobalt there that has given up electrons to oxygen. So that means that you have cobalt ions in a lattice-like structure on the cathode side. So that's the positive side of your battery. But I hear you say, if electrons are ditching lithium and they're heading over to the cobalt side and joining cobalt ions, they are leaving behind lithium ions, doesn't that ultimately become unsustainable because of the electric charges involved? Because if electrons are joining positively charged cobalt ions, they're eventually balancing out that charge, right? The electrons join the cobalt ion, they cancel out that positive charge. Meanwhile, you've got lithium ions back behind on the anode side, and they have a positive charge. Wouldn't that just mean that eventually the electrons would stop and feel less of a pull toward the cobalt side and be pulled back toward the lithium side? Well, that would happen, except the electrolyte in between the anode and the cathode allows the lithium ions, the positively charged lithium ions, to cross over from the anode side to the cathode side. And essentially, the lithium ions settle in between the layers of cobalt, very much in the same way that they had done when they were lithium atoms over on the carbon side. The electrolyte also prevents electrons from passing through it. Otherwise, again, batteries would be useless because we would never convince those little electron suckers to go through a circuit and do work for us. In addition to the electrolyte, there's a non-conductive separator between the anode and the cathode. Because again, you don't want them to come into contact with one another. So there is a real good reason for this, and just as a spoiler alert, I'll just say, boom. On the carbon side of the battery, the anode side, you have a sheet of copper that acts as a collector. On the cobalt side, you have a sheet of aluminum to serve as the collector. The positively charged lithium ions don't regain electrons in this process when they come over to the cobalt side, so they remain positively charged and they stay over there nestled in the cobalt nets. But by moving the positive charge from the anode to the cathode, the pull for the electrons remains steady, and the electron flow or electricity can continue for as long as there are a sufficient number of lithium atoms left on the anode side to give up electrons. But once that amount gets depleted enough, then the battery no longer has enough charge to allow electricity to flow. During the recharging process, the source of electricity, whether it's from a charging cable or a docking station or wireless recharger or whatever, it applies a voltage that's high enough to reverse the flow of electrons, so that now they will move from the cathode side back over to the anode side. The recharging process strips the electrons away from the cobalt, so once again, you have cobalt ions left behind, sends the electrons back over to the anode side, and the positively charged lithium ions escape their intercalation with the cobalt sheets. They move back through the electrolyte over to the anode side. This happens because the positively charged cobalt ions and the positively charged lithium ions repel each other, but the cobalt's locked into place, right? It's like a lattice, so it can't move through the electrolyte. The lithium ions are free to move across to the other side. So they make the journey through the electrolyte back over to the anode, and they are reunited with the electrons, and the lithium ions become lithium atoms, neutral charge. They rejoin with the electrons through the recharging process. Eventually, you get to a point where you're back to where you started, with an anode side filled with lithium atoms and a cathode side filled with positively charged cobalt ions, and then you can use the battery all over again. Now, the layers I just described are not in a flat plane in your typical lithium-ion battery. Like, it doesn't look like a flat sandwich with a cobalt layer on one side and a carbon layer on the other side and electrolyte in the middle. No, instead, these are layers that then get folded over and over and over again, many times, to maximize the energy density of the battery. So if you could see through a battery case, you would see what looks like tons of layers, but it's actually just really a very long series of layers that's just been folded over itself many times. Now, if the anode and cathode could touch one another, the chemical reaction would accelerate rapidly, and it would generate a lot of heat in the process. This is what can lead to a fire or an explosion, and it's why we have strict rules about bringing lithium-ion batteries on board planes. So you might remember a few years ago, when Samsung released the Note 7 smartphone, there were a few incidents of batteries catching fire or even exploding, and it was a big enough problem that Samsung recalled the Note 7 on 2 separate occasions, attempting to address the issue. According to Samsung, there were 2 flaws in battery design that led to this issue. The first battery, which came out from one manufacturer, had 2 electrodes that were somewhat weak and prone to bending, and that meant that if they bent in a certain way, they might actually be in close proximity, in fact, close enough to come in contact with one another, which created a short circuit, which means the electrons could flow through this shortcut rather than through whatever circuit they were supposed to go through, this being the Note 7, and they would do so really quickly, and that would heat the battery up beyond the fail point, and you would have a fire or explosion. Now, the second problem came after Samsung first recalled the Note 7 and replaced the batteries with a new one from a totally different manufacturer, but this battery also had a design flaw, a different one. Apparently, the welding on the new batteries was defective and allowed for a similar short-circuit issue in the replacement batteries, so the Note 7 handsets that were supposedly fixed could still have a similar issue with catching on fire or even exploding. These defects gave Samsung a bit of a black eye, and it really spelled doom for the Note 7 handset, though Samsung stressed that the phone design itself was not at fault. It was just really super bad luck with 2 different battery manufacturers. When we come back, I'm going to dive into how fast charging works, but before I do that, let's take another quick break.
Today and every day, you're doing the impossible, with so little time under so much pressure. And for businesses around the world, it's a real challenge, because increasing disruption comes with increasing complexity. It's time to rethink everything. Using hybrid cloud and AI, IBM is helping businesses take a scientific approach to invent, discover, and solve problems like no one else. Get a new perspective on working in today's world at ibm.com/think. These days, you have to keep everything moving and reinvent the wheel. With a hybrid, you can do both. That's why manufacturers are going hybrid with IBM. With Watson on a hybrid cloud, factories can use AI to automate the little things so they can focus on the next big thing. Businesses that want to innovate at scale are going with a smarter hybrid cloud using the technology and expertise of IBM. The world is going hybrid with IBM. Visit ibm.com/hybrid cloud.
You know, one thing I didn't cover before the break with lithium-ion batteries is that attached to the battery is special circuitry that can control how much electricity flows into the battery during recharging. It's sort of a safety measure, really, and this is important so that you can prevent a battery from overcharging, which could damage the battery. That could lead to one of those short circuit scenarios I talked about. So you want everything to be really controlled when you're recharging to make sure that the battery remains intact and you don't create a dangerous situation or, just cause damage to the battery, which reduces its useful lifespan. So let's talk a moment about USB cables. Only a little bit, because that's just one of the ways that we can use to recharge a lot of electronics, and it's one of the ways that's compatible with some of the fast charging technologies. If you listen to my recent tech glossary episodes, you know that USB stands for Universal Serial Bus. And it's a type of connector and cable system, ports and connectors and cables that replaces a lot of other ports and connectors and cables that we used to have to rely on all the time to connect anything from keyboards or computer mouse to computers or printers, all these sort of things that we need to have all these different proprietary cables for. It effectively helped replace those. And of course, we find USB ports on all sorts of gadgets beyond computers and smartphones. I've got a little shower radio that recharges via USB. So it's on all sorts of stuff. And the USB standard allows for the transmission both of data and of power. But how much power the USB cable can carry depends upon the type of USB port and the type of cable itself. So you're going to find that the amount of wattage or power that a USB connection can carry is going to depend on those ports and the cable being used. Essentially, you're limited to whichever is capable of carrying the lowest amount of power. So while USB cables are largely backwards compatible and USB ports are largely backwards compatible with cables, if you're using an older cable connected to a later port, you're going to be limited to what that older cable can do, even if the port is capable of greater things. That's what I'm trying to get at here. So let's say you're using a USB 2.0 cable to connect your phone to a charging block. The 2.0 standard has a maximum power output of 2.5 watts. That's 500 milliamps of current and 5 volts of voltage. And you multiply those together, you get 2.5 watts. Fast charging technologies can recharge batteries faster by allowing for greater wattage to flow into the battery. So for example, USB 3.0 keeps the same 5 volts as USB 2.0. All right, so the voltage is the same from USB 3.0 to USB 2.0. However, USB 3.0 can carry a current of up to 0.9 amps. That means you get a max power output of 4.5 watts with USB 3.0. This tends to be kind of the default wattage that gets delivered via charging by USB. USB 3.1 and 3.2, they include USB PD. PD stands for power delivery. That can support up to 48 volts, so a much higher voltage, and up to 5 amps. So that means you could have a maximum power delivery of 240 watts. That's a huge leap from 4.5 watts, obviously. 4.5 to 240. USB 4, which is right around the corner now, it will similarly support up to 240 watts of max power. But most devices do not take advantage of this, especially fast chargers don't. The max you see with fast charging right now tends to be right around 100 watts, so not all the way up to 240 watts. Like it's kind of like anything where you think about pressure. and output, you get to a point where the pressure and output will be too much to benefit from. It would only be overwhelming or dangerous. So we don't see fast charging really hitting that 240 watt maximum. At least I'm not aware of one. The ones I'm aware of, the fastest ones top out at 100 watts. So the USB-C cables, those are the ones that have the oval-shaped reversible plug at the end, which removes that annoying trait of having to figure out which way is the right way up for your USB cable. Those are great if you happen to have stuff that has USB ports on them, USB-C ports on them, and they have USB PD built into them. So by default, most USB 3.0 ports just push out that 4.5 watts. So even if you do have a USB-C cable, it's technically capable of delivering more power to a device than 4.5 watts. That's all the juice you're going to get if you have that cable plugged into a standard USB 3.0 port. So again, you're limited by the lowest output of whatever component you're using as part of your setup. Now, if you're curious about what kind of ports your computer has or what kind of USB cables you have, you can always look at the color inside the ports or inside the connectors of those cables. If it's white, well, you got yourself a relic that supports the old USB 1.0 standard. If it's black, it's USB 2.0. A blue port is USB 3.0 super speed. And if it's teal, that means you've got a USB 3.1 super speed or super speed plus. And so that's true with both cables and ports. If you've got both the same color, then you know, all right, well, this is at the highest that these two can support. Complicating matters is that there are numerous fast charging technologies on the market, and each of them has a different maximum power delivery rating. Apple's fast charging tech is built on USB PD and has a 100 watt maximum power delivery. So typically, you actually have to buy a fast charging cable and charger because Apple does not usually include these in the box with its products. Similarly, if you want to connect via a Lightning cable, you would need to make sure that you had a Lightning to USB-C cable and that it had USB PD compatibility built into it in order to enjoy that fast charging capability. Apple's circuitry in their devices like iPhones, it monitors battery charge. So the fast charging ability kicks in as long as the battery capacity is measured at being below 80%. Once the battery reaches an 80% charge, fast charging switches off and the device will charge at the slower standard rate to avoid overcharging. So this means if you run your iPhone until the battery dies and then you use a fast charger, you won't have to wait too long before you're at 80%, but beyond that, you'll see that charging has slowed down significantly. Google also uses USB PD for its fast charging solution, but Google's max power is significantly lower than Apple's. The Google fast charging tech maxes out at just 18 watts compared to Apple's 100. So it delivers electricity to devices with 2 amps of current at 9 volts of voltage. Like Apple, Google also limits fast charging to devices that are below 80% battery capacity. So if you have a Google phone and an iPhone, and they have comparable battery capacities, and you've both run them down to like 20% power, you plug your Apple phone into a fast charging Apple station and your Google phone into a fast charging Google one, you're going to see the iPhone recharge way faster, way earlier. And so that's just how that works. Qualcomm Quick Charge is another popular fast charging standard, and it has several generations of that standard. So there's, Quick Charge 1.0, 2.0, 3.0, all the way up to 5.0. If you were recharging a device with first generation Quick Charge, that being Quick Charge 1.0, you would be limited to a maximum of 10 watts of power. Quick Charge 5.0, by contrast, can deliver 100 watts or more. However, newer versions of Quick Charge are really only found on a few devices. So again, you're limited by whatever the slowest component is. If that component is your actual device, it doesn't matter how good a charger you have or what cable you're using, you're going to be limited by the max that device allows for. And in this case, there just aren't that many devices out there with Quick Charge 5.0 built into them. Quick Charge really does up the voltage. So in other words, this approach is all about increasing the pressure in the system to charge batteries faster. Quick Charge 5 can allegedly charge most phones from 0 to 50% capacity in just 5 minutes. Now, I don't have a device that uses Quick Charge or the recharging accessories I would need to do this, so I can't test it myself, but that's what I've read. If you go back to Quick Charge 3.0 or earlier, you run into incompatibilities with USB PD, but since Quick Charge 4.0, Quick Charge accessories work with USB PD accessories, so you can mix and match cables and chargers from that point forward. Quick Charge also includes circuitry that monitors a battery's temperature, and it has automatic thermal balancing. Essentially, that means it's going to use whichever charging method is going to keep the coolest pathway to the battery to avoid overheating. Next, we've got Samsung Adaptive Fast Charging. The latest version of this supports max power of up to 45 watts in theory, though in practice it appears that Samsung nerfs this a little bit. It tends to be a little under whatever the max would be. Their version is also compatible with USB PD, but limited again to 45 watts. This fast charging tech is exclusive to Galaxy devices. Then you've got Motorola Turbo Power. The most recent Turbo Power 30 product achieves a max power of 28.5 watts. That's built on top of Quick Charge 3.0. So you can kind of think of this as a forked variation of Quick Charge technology. Then you've got OnePlus Warp Charge, which is the most recent version, supporting a max power of 50 watts. And the list goes on. And really, all of these different name brands and numbers gets confusing. And the fact that there are so many different competing technologies for fast charging means it's really hard to compare apples to apples. And I don't mean technology that's coming from Apple in this case. If you want to get really, really basic, you could argue that systems that supply a higher wattage to batteries recharge those batteries more quickly. But that is being a bit reductive, because you have to consider all the elements at play here. What are the limitations of the accessories? What is the battery capable of accepting? Batteries that have special circuitry in them to prevent them from being damaged due to overcharging or voltage spikes are not going to just allow unfettered recharging. So it's not like you can just consistently up the wattage and decrease recharging times. It's not like you could jerry-rig a 500 watt delivery system and you recharge your phone in a minute and a half. That would just most likely lead to overcharging a battery and destroying it, or the phone would just shut it down and limit how much wattage could actually go to the battery in the first place. So the process really has to be controlled, or else things get really dangerous really quickly. That being said, the fact that there are so many different fast charging solutions and the fact that each of these continues to evolve separately means that it's really tricky to talk about fast charging at all. If your phone is a couple of years old, like mine is, it might be that you're maxed out at an older version of whatever fast charging tech applies to your gadget, and that means that you would have to upgrade to a newer device if you wanted something that charged more quickly. And one other thing I should mention, as your technology ages, you might notice that it seems to drain battery life faster, that the battery just doesn't last as long as it used to. There are actually a few different reasons for this, some of which play into the concept of planned obsolescence. That's a strategy that companies use to create a planned life cycle for products, partly in an effort to get you to buy the next one of those things. But there are some other things at play beyond just corporate strategy. And one is that when you buy, say, a smartphone, you're locked into that hardware. Unless you are a real DIY tech head, your phone is pretty much going to stay exactly how it was when you bought it. And yet the companies that created the operating systems, like Apple and Google, they're going to keep evolving those systems and releasing updates to the operating system that allow for more sophisticated and complicated apps. And these updates might place a greater demand on older hardware that, wasn't optimized for these newer versions of the operating system. And as such, Older handsets will see battery life suffer because they're not optimized to handle that. In some cases, companies will actually throttle processor speeds in an effort to offset battery drain, but users tend to hate that too, right? There's nothing like finding out the reason your phone seems to be slower now is because the company that makes your phone made it slower on purpose. Even if that purpose was to give you more hours of battery life, people hate that. Another reason battery performance declines over time is that in the discharge and recharge cycles, there's typically some buildup of what's called solid electrolyte interphase. This happens as lithium, electrons, and the electrolyte, as well as some organic solvents, react during the recharging phase, and it creates little buildup deposits on the anode side of the battery, which effectively locks down some of the lithium in the battery. And because that lithium is locked down, it means there's less lithium atoms to release electrons, so it means your battery's max charge has diminished, because you don't have as much of the active ingredients, if you will. In addition, if you fully discharge a lithium-ion battery, some of that lithium will end up on the cobalt side and form lithium oxide. Some of the cobalt will form cobalt oxide. And effectively, that removes the lithium from the process and it locks it in at that point. So you have reduced capacity because of that as well. So you don't want to drain a lithium ion battery all the way down to zero if you can help it. Older rechargeable batteries had a similar issue called the memory effect. This was prevalent back in the nickel-cadmium battery days. While it's generally a good idea to recharge lithium-ion batteries before they drop below, say, 30% charge in order to avoid those lithium oxide buildups at the cathode side, if it's a nickel-cadmium battery, it was a good idea to actually use them until they were fully discharged. So, of course, that's led to some confusion, right? Some people are saying, well, should I wait until my battery's all the way to zero before I recharge it? Or do I wait until it's like at 30 and recharge it? Well, with lithium ion, it's better to do it at around 30. But with nickel cadmium, you wanted to use that battery as much as possible because if the batteries were not fully discharged before recharging, you could see your battery capacity decrease. This is easier to understand with an example. So let's say I have an old nickel cadmium battery and it's charged up to 100%. And I run my electric podcast pruner until the battery gets down to 25%. And then I recharge the battery back up to 100. Well, there's a chance that my nickel cadmium battery will behave as if that 25% charge was actually 0%. And now it will remember that 25% is really zero. So instead of having a 100% charge, I effectively have a 75% charge because it will never go all the way down to zero again. It'll get down to 25 and then the battery goes dead as if there were no charge left in it. That was a problem with nickel cadmium batteries. And it meant that, your battery charge would severely decrease after a relatively short amount of time. Now, as I said, that's not really the case with lithium ion batteries, which tend to see capacity reduce if you do run the battery until it dies and then recharge. But even if you use best practices, there will come a point where a rechargeable battery will just outlive its usefulness. It might take thousands and thousands of charge cycles before that happens, but it will eventually happen. It's just a good idea to practice good behaviors because that helps extend the useful life of batteries as much as possible, which is a good thing just to avoid being wasteful. All right, that wraps up this episode about batteries and fast recharging. I know it's a big mess. I didn't get into too much technical detail because really when you boil it down, it does get down to how much wattage do these different methods apply to batteries and how fast can batteries accept that. And at what point do these systems cut off fast recharging to avoid overcharging a battery? That's really what it gets down to when you really dig down. If you have any suggestions, like Perez did, thank you again for your suggestion, you can send them to me on Twitter. The handle for the show is TechStuffHSW. And I'll talk to you again really soon. Tech Stuff is an iHeartRadio production. For more podcasts from iHeartRadio, visit the iHeartRadio app, Apple Podcasts, or wherever you listen to your favorite shows.
Have you heard of ClickUp? It's the fastest growing productivity tool that's saving people 1 day a week by bringing all your work into one place. Loved by 200,000 plus teams in companies like Uber and Webflow, ClickUp brings your tasks, docs, goals, chat, and more into one place to help you get more done. ClickUp is free forever. So sign up today at clickup.com/iHeart.
The future of driving is electric, and it's coming fast. That's why General Motors and EVgo are adding more than 2,700 new fast chargers across the country through 2025 for the benefit of electric vehicle drivers on the road. And best of all, these stations will be 100% powered by renewable electricity. It's all part of our commitment to make convenient fast charging accessible for everyone. Learn more about how GM is developing an all-electric future at gm.com. Everybody in.